Yeah, perfect. Okay, mute, mute, mute. Yo. Okay. New Woods. Yeah, midnight.
So downstairs. Can we get you a chair?
What is going on? Okay, James, you should be receiving the R file shortly. Thank God. Anywhere that works for you. I'll be moving around up here, so yeah. Yeah, eventually I got to pick off. Thank you. No, thank you though.
Okay.
Yeah, as soon as you can register into the meeting, that'd be great. And then I'll give you co-hosting capabilities, and then you can help handle with the chat room. I need to send them a file because it looks like half of them don't have it. Although I don't know. No. And I'll send it to you in case this keeps happening. Gosh, I feel like I'm browsing the worst web page with the number of things that pop up. What's this? Oh, there's Don. Perfect. Don is co-host. I do. Okay, great. And Don, I just sent you the R file that some of the folks online are saying they don't have a copy of. So if you can handle sharing that, that would be terrific. Thank you. Let me close that. Okay, we'll go ahead and start collecting the surveys. Okay. Sorry? Yeah. Okay. Okay, thank you, folks. Those of you who did fill out the survey, those of you still working on it, that's fine. I can pick it up at the end or during the break. As I mentioned about 10 minutes ago, but I'll say again for those of you who came in since then, welcome to our workshop. This is the Collaboratory Workshop, Introduction to Programming in R. My name is Alex Brummer. I'm a postdoc here at UCLA. I work in sort of biomathematics, ecology, evolutionary biology departments. I will admit up front where you might have a few hiccups as we get this started, balancing between running the new Zoom for the online version of the course that we're doing. Scattering my brain a bit. So a few things that I want to say about the workshop itself and then about R. Don't touch that again. Well, let's say, I guess, a few things about the workshop while this is coming back. A combination of looking at how this R workshop feeds into the sequencing workshops that the collaboratory also offers after this, as well as the very distributed backgrounds of everyone in here in terms of the departments you're coming from, but also your program and experience. I made a couple of decisions. One decision, I'm just making, we're going through this workshop under the assumption that everyone in here has zero experience in programming. So for those of you who do have some experience, please be patient. Hopefully you'll still learn some interesting things as you go along. For the rest of you, this is mainly being done so that we can all kind of be on the same page and footing as you go forward. Also, in that sense, I know online we still say that day 3 of this course is nothing but bioconductor, but you may have seen in the email that I sent out that the anticipated syllabus doesn't have anything about bioconductor or sequencing for that matter. I made that decision based on, again, off of the fact that there's a very distributed background of individuals in here, and that the collaboratory offers 3 more workshops on doing sequencing analysis with R. So for this workshop, the introduction to R, we won't be doing sequencing. We're going to be focusing on very general data and learning how to use R in that vein. If you're interested in using R for sequencing, I highly encourage you to register for the other workshops that we offer that are nothing but using R for analyzing sequencing data. So, a few words about R and how I use R. Also, I'll mention, I don't actually do sequencing analysis. My background's in physics and mathematics, and I do more like a first principles modeling of the cardiovascular system using fluid mechanics. My training, I'm not a traditionally trained computer scientist by any means. I took a couple courses on programming and then picked up the rest that I needed to learn along the way. My hope is that through this course, you'll feel competent with what you've learned, that you're able to kind of navigate the resources online, the resources that we provide, and you'll also be able to, pick things up along the way as you move forward with your work with R. R used to be primarily a statistics language used for just analyzing data. The way it was structured, it could run fast on large data sets. But R has become much more of a kind of programming language for more than just statistics. There's been a lot of interest in using it from many people from different backgrounds. To give you an example of some things you can do with R that aren't just statistics, as I mentioned, I study the cardiovascular system. So one thing that I do with R is I take, we call it segmented medical imaging data. So these are from a chest CT scan of a patient of their lungs. And we have separate software that runs in a different language that goes through all of the medical images, the images, and identifies which pixels correspond to blood vessels and which pixels correspond to non-blood vessels. And then in R, we can actually take that data and then reconstruct the lungs and in a 3-dimensional rendering. So R, this is meant to just kind of be proof by example. R is becoming a very powerful language for a lot of the things that it can do and is capable of. So there's that announcement. Great. How will this workshop be structured? I basically teach this the way I was taught, which is talk, type, follow. So I'm going to be speaking about R and the things that we're learning and doing with R. And then I'll be typing along in this scripted prompt that you all have a copy of. And we get to a blank section, and then I'll type what goes into the blank section, and then you'll type and follow so that you get a sort of tactile experience in learning the program. And then you also leave with a copy of notes from the class. So you kind of have, it's like a worksheet, you can think of it. as. But don't worry if you miss any part of the worksheet that gets filled in. I know sometimes as we're scrolling, you might lose the part that we passed by. Feel free, of course, to raise your hand and ask for me to scroll back up so you can see it real quick, or for me to repeat what I said we were typing. But if you get fully lost in what was typed at the end of the day, each day I send out a copy of, you could think of it as like the master solution set of this worksheet where all of the expected responses are typed into place. So each day you'll come in with a blank version. End of the day, I will email out the non-blank version as well as my solutions and versions to any of the prompted activities for coding. Ideally, we'll spend each day, we'll go through a bunch of different topics that we're going to be learning about, and then at the end of the day, I'm trying to reserve time so that you all can break out into small groups and actually work on programming some of your own things. There's prompted questions, so it's a try to graph this or try to program this. I'm still dialing down the pace for this workshop and how to best go about that. So ideally, I'm hoping we have about 30 minutes at least, maybe even 60 minutes at most for that each of the days. We'll just see how that goes though as we move forward. Okay. Also, there are many great resources for R Online. I'm going to point out some of those throughout the workshop. The Collaboratory has currently some traditional slides talking about R and some of these resources for R Online. But we don't have posted online quite yet actual set of tutorial notes. But as I mentioned later on, I'll point you towards some other resources online that I think are pretty great. Before we delve into now RStudio and R, are there any questions from anyone in the room? Yes, sir. I'll get that. The next thing I'm going to start with real soon. Any more questions though, like structural questions about the workshop itself? Okay, great. Well, let's see. Okay, so first question, what's the difference between R and RStudio? If you hadn't already downloaded either of these, you'll have seen in the email your instructions to download both R and RStudio. So R is, you can consider it as the language, and RStudio is the interpreter. By language, you can think of this as, it's like the syntax, the grammar, the structure, it's the rules with which we have to write the language that we're typing. And then RStudio, by interpreter, it literally reads through all the text that we've typed, it interprets it, and then it runs it, so to speak, under the hood on your computer. You can run R from your command line or your terminal. Let's see if I'm not even gonna go there. Actually, some people, it really depends on who you ask in terms of preferences for running R from either a nice, graphical user interface, you might say, like RStudio, or just run the command line of the terminal. In that instance, it looks more like what this bottom screen is here, where there's this flashing cursor and all the previous lines of code that I've ran. Some people like that because it's simpler, there's less bells and whistles. I find for teaching purposes though, using RStudio is quite advantageous. And actually, my personal preference, I use RStudio also because I like the bells and the whistles. So some more about, let's go through the script. Our overview, here we go. We're going to focus this workshop around analyzing data. So this perspective comes from here. R reads your data, for example, an Excel file or a text file, or a CSV, a comma separated or tab separated version of the file. And it makes an image of it, which is stored temporarily in memory. That means when you edit your data through R or RStudio, you're only editing this image, this copy. You're not actually editing your original data. Unless you write to the file, then you might be editing it. Don't worry, we'll talk about that soon. From here, you can create graphs, you can modify the data sets, you can write it back to the permanent file. This is all called non-destructive editing. You can also create objects like matrices or what we call data frames directly within R as opposed to reading them in from a separate file. As I tried to show with that quick demonstration, R can do quite a lot of things. We run R by writing what are called script files or .r files. That's the file I shared with you. It's the file that we're kind of reading as we scroll down here. And with these files, as we say, you can keep a record of everything you've done to manipulate and analyze your data. It can be beneficial if you share that with your colleagues or you come back to return to your project in the future. So let's get to know RStudio and the R functionality, the RStudio layout. RStudio is a nice visual interface for R. You can open up R on its own, the default visual interface. There are 4 window panes for RStudio. I'm going to switch the script pane so I can show you all 4. There is the script window in the upper left, which is where we're going to be reading and typing most of our code, and it's where you can save your code easily. On the bottom left is what's called the console. Anytime you run a line of code, the code that you ran is going to be printed, so to speak, down below in the console, and then the output from running that's also going to be printed out in the console. In the upper right, there's opportunity for a few windows here, something called the environment and the history and connections. For our purposes, we're mostly interested in what the environment is, which displays all of the variables that you've defined in your most recent session. And I've been doing lots of analysis of long data here, so I have lots of variables open in the session. I'm going to press on the little broomstick button here and empty the environment, clear all the objects from there so that there's less mess present. So now it says the environment is empty. We haven't defined any objects or variables. We haven't read any files into R just yet. And then finally on the bottom right is where any graphs that you may make will be printed. If you print them within R, you can also print them straight to file, which we'll do. But for quick viewing and analysis, you have plots made down in this bottom right pane. There's a lot of packages for doing different types of analysis that don't come with R when you download it or with RStudio when you download it. And so there's a package manager down here that allows you to load those into your current session or see which version you most recently have downloaded. And then there's also the help menu, which we'll talk some more about later, but you can search the help menu to try and get help. It can be hit or miss. Sometimes it's perfect, sometimes it's utterly useless, and then you need to go online. That's pretty standard and just how it is. Okay. Now, before we talk about scripts, the most important part is personalizing your RStudio experience. So if you're on a Mac, please click on RStudio, go down to Preferences. If you're on a PC, Windows, please go to Tools, I think is where it is, and then find the Preferences button. From Preferences, we can go to, I believe it's Appearance. Yes. And in the Appearance option, you can modify the theme of what's called the editor, which means you can change the color palette to be something that's more reminiscent of Matrix or just more fun or easier on your eyes. There's quite a lot of options here. I just like to point this out early on so that you're not all just stuck with the default page for the next 9+ hours. I'm using Xcode as this just hideous white background, black text, just to make sure everyone in the room can hopefully see the text. Folks in the back, give me a quick thumbs up if everything that has been on the screen has been readable, legible, and big enough so far. Perfect. So I'll keep using that. Great. Okay. So what is a script? This is stupid. I wrote this at the front a while ago and I still can't. Okay. A script is like a story about your data analysis. It is written with comments in plain English. Comments are preceded with these pound signs. Comments are very helpful. We'll talk more about comments, but comments don't get read by R. Preceded by the pound hashtag symbol and code in the R language. R reads the story, ignoring the English that's preceded by the pound symbol, and performing the actions you instructed it to take. This is running, executing, or compiling the code. You can execute code directly in the console by hitting return. I can type 5 + 5 here in the console, hit return, and R runs like a calculator or just runs the code in the console. Or by writing scripts, as we're reading in this file, which keep a record of every step of your analysis and allow you to rerun the analysis later, maybe on different data sets or modifications. To run the code from your script, If you want to run any code that the cursor is in line with, you just let the cursor sit in that same line and press Command Return on Macs or Control Return for PCs. To run multiple lines of code from a script, just highlight the lines of the code, and then it's the same. Control Return on PCs or Command Return on Macs. The script window, this is where you develop your scripts. There are some nice automatic functions included like color coding, indenting, automated bracket, quote closing, tab completion. As you find, you may not remember the name of the functions or the name of the variables you have. If you can remember the first few letters and then press tab, R will pop up a whole menu of options you can try and tab complete with. You can have multiple scripts open, working with them at different times. For example, here's the master script I have in another tab, and here's the blank one we're back working with. There we go. Console window, bottom box. This is like the regular R console window that you would have if you ran R from your command line or your terminal. This is where your scripts run, so to speak, and where visualized results are returned unless you're making a graph. Yeah. Bottom right window is our help files. Upper right, as we mentioned, is your environment. Great. Okay. Moving forward. How to ask R for help. Obviously, you can go to the help option in the bottom right pane and type in the search key you're looking. Oh, question. Yes.
Yeah, I have a question. How do you make it so that the line doesn't go run on?
Wrapping. Thank you. Yes, that was the first question we had last week for the Python workshop also. I need to just make that the first thing we do. Also go back to preferences so we can have text wrapping. And then this should be in general. That's not it. Let's try code. Soft wrap, there it is. So under the code tab, general, look for this box that says soft wrap R source files. Check that box and that should give you text wrapping in the script files. Thank you. Any other questions from folks?
I have a question.
Okay.
Can you hear me?
So, asking R for help. You can ask for help by typing the name of something in the search bar in the help pane, or you can also ask for help by using R's pre-made functionality. And I left these ones here. So there's a few ways to ask for help. So we can, maybe we're interested in, we want some help for how to use the mean function. R has a function in it called mean for calculating the average value of a distribution. There are two ways you can ask for help about it. You can type a question mark and then MEAN for mean, and then leave the cursor in that line and press Command or Control Return. And then you'll see in the bottom left, R ran the line of code question mark mean. In the bottom right, we have opened up the help page for the mean function. Use another instance question mark plot. So Command Control Return on question mark plot, and now we get the help menu for the generic plotting function in R. You can also put that function and put it inside of a call of the help function itself, right? So functions have names, and they have parentheses, and then they have arguments. We use from math, I mean like f of x, y. We use functions in programming the same way. The function has a name, it's the help function. It has parentheses, and then inside the parentheses go the name of the thing you want help on, the mean function. So we can type help, open parentheses, mean, close parentheses, and then press Command or Control Return, and R again sends us directly to the help page for the mean function. And then if you want to get meta and have fun, you can put the name of the help function inside a call to the help function and press Command or Control Return, and then what shows up in the help page is the documentation page for the help function.
Do you know what that is on PC?
Sorry?
Do you know what that is on PC? Command Control Return.
Sorry, I'm saying Command Control, so I'm trying to be inclusive of both Macs and PCs. On Macs, it is Command Return. On PCs, it should be Control Return.
Oh, okay.
Which one? Ah, yes. So of course, you can use the mouse and scroll up and click on the Run button. However, as you start to get like really zoned into your coding, sometimes it's nice to have to use the mouse as little as possible. So I'll be speaking in terms of using Command Control Return. But yes. That option exists. Okay, so. Right, I said this before, say it again. Note that sometimes the documentation or the help is useless, and searching the internet for additional documentation or help is necessary. We use Google and strategic searching. This includes the name of the function command object. If you have errors, you just search the error message. We'll practice with that some more later on in the workshop. I just want to drive that message home. So, moving forward, we're going to go straight to importing data. As what we call data frames. And I'm realizing now for folks who didn't have the R script, you also don't have the R data files we're using for the day. So Don, I'm going to send you copies of these data sets. And then if you don't mind sharing these with the folks online who are bound to say, I don't have the data set, that would be great. Hawks. Iris. Also, James, I'm sending these to you as well, since I know you don't have great, perfect. Let's see, attached. Oh, where's the top of that? There, send. Great. Okay. So in addition to having received the script, you should have a couple of data sets that we'll be using today. We're going to now load one of those data sets into RStudio to interact with it. We're going straight to this because basically what I want to do is for us to learn how to use a bunch of different aspects of functionality with R through some sort of guided discovery activities and analyzing data. So starting with data. So how do we load data into R? First, we need to learn about the working directory and set the working directory. Setting the working directory simplifies importing and exporting. You can imagine this is like navigating in Finder or any sort of folder, directory, or path. We want to basically tell R where all of our data files are in a given folder. So when you ask R to import or read a file or export or write a file, it will point automatically to what we call the working directory. So you don't have to keep typing in a new path or directory every time. The easiest way to set the working directory to the script file location. So in RStudio, we'll use the mouse for this. Go to Session, the Session button in the upper part of your screen for the drop-down menu, and then go to Set Working Directory. And you're given a couple of options. Source file location means that the location of the script that you're actively in will become the directory. So if this file is saved in the same place as all the data you want to work with, then that's fine, that works. Alternatively, you can just click Choose Directory, and then it opens up one of these windows where you can navigate to the folder that you want to use. And I'll use that for today. So I'm going to scroll way back and find where I've saved my copies of what we're using for today, the data sets. I would encourage you to go find where you've saved those data sets so we can use them. So I have day one. Great, and here's our script files, and here's the two data sets, Hawks and Iris. So once I found the folder that I want to use for the working directory, I just make sure that I've clicked on it, and then I click Open, and then you'll see R automatically in the console printed out a command, set WD for set working directory, and then here's the name of that path. The Ogre Dropbox Teaching Collaboratory, or day one. Day one is the folder where I have the data sets. Which means if you want to set the working directory typing, this is the command that you would actually type. You'd use that set WD function, and then you'd enter in the name of the path to your folder, which I've included here, except I changed the name of this path, so let's modify that. So you can type set working directory. Here's the full path, the absolute path, /users for me, Alex, work, desktop. No, not quite. That's O Drive, Dropbox, teaching. I shouldn't say this like it's what you type. You will be typing wherever you've saved your files, in this case. Workshop, day one. Yeah, so this is an example of you can type the command that was printed into the console alternatively, and then that should also allow you to set working directory. Great. If you got something wrong in what you typed, maybe I forgot to include the 1 in the day. and I try to run this command, I get an error message. R tells me error in that use of set working directory, and then it tries to give me an interpretation of this. It says cannot change working directory. That message means basically I probably got the path wrong, or that path doesn't exist. So I should double check exactly what I tried to type for pointing to that directory. The one downfall of trying to do this by typing is that you can easily mix up your letters for the path, but R will try and point that out. And then when it executes cleanly and basically anytime you don't get an error message, then whatever you told R to do, it did. Which means it either did what you wanted it to do, or you accidentally told it to do something you didn't realize was what you wanted it to do, and it did it anyways. Okay. You can also ask R what the current working directory is in case you forgot. And that is by using the command get wd or get working. Why are there entries? Okay, is it everywhere? That's going to be a problem. This should be the blank. That would be funny. Okay, if you type get wd open close parentheses and run that line of code, then R prints out what the working directory is for you. So you can know if you're working in the directory that you want or not. Finally, you can ask R what all the files and folders are that are contained in that working directory by using the dir open close parentheses command for directory. Command return, and then printed in the console, there's our running of the command dir, and then there's a list printed of all of the objects that are in the directory. There's these two R script files, there's an image that I made from graphing, there's something called greetings everyone, and then there's the CSV files for the data that we're going to be working with. Quick question, I hear folks typing, but I'm not sure, are your copies of this file blank, or do they have things typed into them? For example, if I scroll down, everything's typed in. Cool. That will be different tomorrow, but today the answers have been revealed. Cool. All right, that means we're going to move fast. Okay, note you can use the command set working directory as we did. You'll notice sometimes this tilde symbol shows up when you're setting the working directory. That has to do with absolute versus relative paths. Basically, the tilde allows you to skip a whole bunch of the preceding folder names in the path you're working with, and you can just navigate to a different folder in the directory you're already in. But if you need to navigate to like a different parent folder, then you would type the absolute path. But of course, when in doubt, just using the mouse and navigating through the session and set working directory option with the Finder window can be pretty foolproof. Okay, let's read in a file as a data frame. So now we're going to load to our field data we have into R for some analysis. So we've set the working directory to the folder that contains the iris.csv data as described above. We're going to use what's called the read.table function to read in the file and assign it to an object called iris data. Said a lot of things there. So when we import the data, we want to assign it to a variable, give it a name, so that R stores it, a copy of it, in RStudio. So the command, okay, we would have typed iris, and then we use what's called the assignment operator, which is a less than sign with a hash, a hyphen, sorry. Looks like an arrow pointing to the left, because we're assigning the thing on the right to the name on the left. Then we have the instance of this read.table function, open parentheses, and then we have all these parameters we're going to fill in about the function that we're going to read. I'm actually going to delete these and mark them anyways. And say some words. So first, I'm using tab complete. So I am inside this function, I press tab, and RStudio displays to me all the possible parameters I could use for reading this file into RStudio. We're going to focus on the ones that tend to be the most important, such as the name of the file. We have to tell R what the name of the file is that we want to read. So say file equals, I'm going to add the file names, they start in quotes. I'm blanking on the name. I don't quite remember, but I got the first part typed in quotes. So R is going to go into that folder and try and find all the things in there I might want to try and read in. Tab complete is amazing. So we want the iris CSV file, so I can click on it, and now it types in, it completes for me iris.csv. Okay, comma. The CSV file, CSV stands for comma separated version. I think the V is version. Most important, it's comma separated, so I need to tell the read.table function that it is a comma separated file. So I can use this SCP or the sep parameter to type in quotes the comma character so that R knows to look for commas, and every time it finds a comma, great, that defines a new cell, or that goes, we go to the next row from there. A couple more parameters. Header equals true. You may or may not know this until you actually look at the file itself, but the file has column headers, names for all the columns in the file. So we need to also tell RStudio that that is the case. Otherwise, it would think of that first row as the first entry in the data as opposed to the name of all the columns. So we say header equals, in all caps, true. The first row of the data file are the names of the columns. This data file also has row names in it. So I'm going to tell R which column in the data file the row names correspond to. In this case, it's the first column. And that's it. We'll run this line of code by pressing Command or Control Return. And now we'll see something's changed in our environment pane in the upper right. There is something called iris. That's the name we gave to this running of the command when we assigned this data to the variable iris. And then there's some information about it. It says there's 150 observations of 5 variables. And if we want, we can click on this little right pointing arrow and it tells us, oh, here are the names of all those different columns. And then there's something num, well, we'll learn about that later. Factors, we'll talk about that too. And then there's a bunch of numbers. It's giving you the first few entries in each of those columns. So there's another reason why RStudio can be nice is that it gives you some nice summarizing data information about the data that you've defined and are working with in R. So I'd said assignment is important. The use of this arrow sign and then this other variable name are essential. Why? What if I deleted this from the environment, so the environment's empty, and all I typed was read.table. I didn't have the assignment part. I didn't have the iris part in there, and I tried to run this line of code. I do that. Nothing is saved in the environment. All that was happened now in the console is that RStudio read the file and then printed all the file information in the console, which is convenient maybe if the file is not too large and I want to get a quick look at what's inside the file. But it's inconvenient because now I can't interact with the data, right? This is why I'm saying we need to assign the data that we read into R to a variable so that it exists in the environment. Now the environment's empty, and all I have is this printout of what's in all the data that I have in the file. So instead of printing all that information into the console, I want to save it as a variable named iris so that I can interact with it. So going back to Command or Control Return, so I have this variable find. Great. Now, oh, yes. This part, interesting. That might have something to do with a version you downloaded. But it's, I mean, you still have, it's defined. Yeah. And is it under a heading data? Yeah. It should be, if you have more problems in the next few lines, then it's a real problem. Now it sounds like it might just be a difference in version, or maybe in the preference settings, in terms of like what information is summarily presented. Okay, let's see. Let's view the data in the console. Okay, as you saw, we could use the read table function to view the data in the console. There's another thing you can do now that we've defined the data as a variable named iris. You can use the view function with a capital V, i.e. W, and then we put the name of the data file we have, iris, that variable, representing the data inside the function, run that line, command or control return. And then what is now printed as if it's another script file, but it's just a fancy rendering of the file, of the data itself, is a rendering of the data. So we have, it looks like it's another script file up here as we toggle between the different tabs or the scripts, but it's not. It's just a fancy way of viewing the data within RStudio. And now we can see the column names, sorry, sepal length, sepal width, petal length, petal width, the species names for all the data. And then there are row names, which are just indices, counting out the rows. And then in the column here are all the data values. You don't get, when you type view, the name of the file, you don't, that doesn't pop up. A blank window. When you have, does it say there's 150 observations and 5 variables? Ah, okay. So something about the use of this function didn't quite go so cleanly. Or it might have been that the name of the file wasn't copied correctly, or your working directory. It's good? Awesome. Perfect. Sorry, Don, made you get up. Yes.
Could you explain the header and row names functions again, real quick?
Right. And this isn't to be annoying, but so these are parameters inside the read.table function as opposed to functions. So we have these header and row name parameters. And basically, so in the data file we have for this data, the data has row names, sorry, on the far left, and it has column names or header on the upper for each column. Like that's in the CSV file of data, just how it was recorded and structured and sent to us. When you read data into R, you need to tell it whether or not there is a header and whether or not there are row names. If you don't, if we say there is no header, we'll make this false. And the row names, we'll leave it blank. Oops, whoa, into the bottom. We'll leave row names, not blank, but we just won't provide an entry for row names. So now we'll run this command. Okay, interesting. Now in the summary it says the 151 observations and 6 variables. We've now added a row and a column to this data file. If we view it, command control return on view iris. Now see this, we don't have column names, it just says V1, V2, V3, V4. V I think it's for vector here. And instead this first row, what were the column names, is now treated as if it's data. And we have this extra column of the counting integers, just counting all the rows, and it made a name, a column for all the row names on the far right. So anytime you read data into R and your data looks funny like this, it means that you forgot to tell it that the header existed and which column had row names. So we'll go back to true for the header. Correct, no cells, not like Python. Row.named equals 1. Sorry, some of the folks in this room were with me last week for the Python workshop, and as we're learning about R, we're learning about the nuanced differences between the languages, which are both subtle and pronounced. Okay. There was a thing I was gonna say. Yeah, I'll come back. Okay. Okay, well, it turns out we read CSVs so often into RStudio that some folks got frustrated and wanted to just make their own read.csv function, so they don't have to keep typing all those parameters. If you're always going to be reading a CSV file, why do I always need to tell you that it's separated with a comma for assumptions about the headers? So if you want, you can also just use the read.csv function. You define the file parameter the same as before. We do still need to specify the row names if you have a row names column, but it checks automatically for the header and already knows that you're going to have commas separating the values in the file. Yes? This table?
Yeah.
No. I mean, you can manipulate it, but it doesn't dynamically update the viewing of the table. You have to rerun the view table command, I think, or at least click out and click back into it. And then it'll update and reflect any changes you've made. Okay, since we already have used the iris name as one variable name, I'm going to use a new one so we don't overwrite the image of the data in RStudio. So I'll call it iris2. Press command return, and we see we have another copy of the data, the same as before, only it's just got a different name. But I loaded it using a different function that performs the same task. Right, that reminds me what I was going to talk about. We're going to be analyzing this data throughout the rest of this workshop. We've been viewing, right, fine. So real quick, since we may not all have backgrounds in ecology, let's quickly just point out what this data set is. The data set's called iris. It's for iris flowers. There are 3 different species of iris flower data in here. There's Setosa, Versicolor, and Virginica. All that matters is that those names are present. We'll use them more later. And then the variables that were measured for these flowers were the sepal and petal widths and lengths, which have to do with the width and length of the leaves, the green tissue on the plant, and the widths and lengths of the flower petals on the flowers on the plant. Any questions? Cool, all right. So, viewing your data frame as a spreadsheet. Right, yeah, sorry. In addition to typing the view command, you can also just click on the name of the variable in the environment, and that acts as if you typed and ran the view command. You'll notice in the console in the bottom left, when I when I clicked on iris2, then in the console in the bottom left is printed the command view iris2, and then in the upper left is automatically displayed the table iris2 for the data there. Okay. Let's see. This is this RStudio has changed. It no longer only displays the first 1,000 rows of your data. It will show as much as you want as you keep scrolling. There's only 150 here, so it stops. And there's a view command. Why is this out of order? We did this part. That's fine. If you're trying to dynamically view, I'd like that to go away. If your data set's really large, hundreds of thousands, millions of rows, then trying to view and scroll through the whole thing in this window can be arduous, to say the least. Not worth your time, to say the most, because we're going to learn how to access and view different chunks of the data as you need. If the data is small, this isn't so bad, but once you get into the thousands of rows, it can slow down as you're scrolling, and it updates to show you what's in those different rows. So some basic data functions, functions to tell you information about your data. The str function will print what's called the structure of the data frame. Str is short for structure. Gives you information like the number of rows and columns, the names of the columns, the class of the columns, or what types of data information it is. Are they numbers? Are they words? So we'll try this, str iris, command return, and in the console is displayed. It's a similar actual version of the information that's shown in the environment when you press that little arrow. Actually, it's the column names, classes, a few instances of the data in those columns. Yeah. If you want to look at just the first 6 rows of the data to see how it looks, you can type head for header of the data. So we have your head, parentheses, iris, command or control return, and you're printed out the column names and the first 6 rows in each column. Since my font type is so large, this is wrapping around, so it only shows the first 3 columns and then comes down a row to show the last 2 columns. Maybe if you want to look at the last 6 rows of the data, you can type tail for the tail end of the data set. So command control return on the tail iris command. Same thing as before, but now just the last 6 rows of the data as opposed to the first 6. If you want to have the names of the columns accessible or viewed, you can use the names function. So we have names, iris on the inside. Command Control Return, and what are printed is just a list of the names of the columns, each in quotes. Alternatively, you can use the call names function for column names, and the row names function for the row names, which in this case is just the numbers 1 to 150. But if maybe you have actual text as the row names in that case. Yeah, it comes later. Names always just gives you the column names because of the type of data that we're working with. It won't give you the row names. So if you want to access row names, you have to actually use the row names function. Yes?
We have one question online. People
Certainly.
want to know if they read it in their data file and it reads it as a factor, but they want it as a number.
Yes,
How do you change that?
we're getting there. It gets us into the realm of coercion or conversion, but where you convert the types from one to another, and we'll absolutely get there. Okay, so next part, accessing the data in your data frames or indexing. If we want to access certain columns in our data frames or certain rows, we need to perform a task that is called indexing. There are many nuances to indexing, and it's an extremely powerful tool. I tend to argue this might be the most important thing you can learn because everything else we do is based off of indexing and indexing of your data. And it's also how you get access to the data you want to work with. So we will say many things about indexing as we go, as we revisit it, but for now we're only going to focus on the most important parts. Okay, so there are two primary ways of accessing different columns of data in our data frames, our CSV files that we write into RStudio. One method is by using called matrix notation, where we input the numerical position for the row and the column separated by a comma for a given cell or entry in the data. Right, if you think about a matrix, right, these big two-dimensional objects, they have rows, they have columns. We can count starting from the upper left, we can count to the right, we can count down to access, like Battleship, right, the location of an individual cell of data. So if we wanted to print or view the 10th row in the 3rd column, we would type the name of the variable that we want to index, the iris data frame, and then using square brackets to index, not parentheses, but square brackets, we type first the row number and then the column number. And that's universal. It's always going to be row, comma, column. That'll never change. And, Python people, R is not a zero indexed language. R starts counting from 1. So if you want the 10th row, you type 10. If you want the 3rd column, you type 3. If you're confused by that, don't worry. Well, it's great. I love non-zero indexing. So iris brackets 10 comma 3, command return. That value is 1.5. That's the value in the 10th row of the 3rd column. You can verify it if you want by actually going to the data frame and going, okay, 3rd column is petal length, 10th row is nice, there's an index, there's a row name for 10, it's 1.5. Great, looks correct. Maybe you want to print out an entire row and not just look at one entry in that row. But you know, right. So you want to view all the data in every column for a given row. Then what we do is we leave the space with a column number blank. And then all we specify is the row number. So we want to view all the information in the 10th row of data. So we type iris square bracket 10 comma blank. And you can fill it with spaces if you want. You can even put in a line break. I wouldn't advise it, but you could. R doesn't read a white space like Python. Sometimes I'll put an intentional space just so that when I view this, I know that I left it blank for like my own purposes when I read it. But it's all your call. So command return on this iris square bracket 10 comma blank, and now we have every entry from that row. And then RStudio is, because of the type of data we're reading, it also prints out all the column names as well, which is convenient if you're maybe looking many rows at once and not just one row at a time. On the other hand, maybe you want to print an entire column. most useful for making graphs if your columns are maybe all the data along one axis. Same idea, but now we just leave the space for the row number blank. So if we want to view a whole column, maybe column 3, then we type iris square bracket blank, comma 3, command return. And now printed are all 150 entries for the third column, but this time the name of the column is not printed, just all the column entries. Okay. Any questions on this matrix style indexing? Yes.
So I just want to know if you can index both at the same time. Column name.
Yes. Yes. That is the next thing. That's perfect. You all have great questions. Segue questions are so fun. Okay. The other method of accessing entire columns of data is to use the $sign and then the name of the column that you want to access. So for example, if you wanted to access the species column in this data frame, we would type iris, the name of the data file, $, species. And tab complete works here as well. So I can start, even with just iris, I can start typing IR, tab complete says, oh, what do you want? Iris, iris 2. I don't know why iris 3 is an option. And then I say, oh, I want one of these columns, $. I can't remember which column oh, great, thanks. I didn't have to type tab. It just used predictive typing. And it gives me all the names of the columns in the data frame. And so I can go to species, press command return, and then it prints for me all the names of the species in the data frame. For the box?
Yeah.
Tab. Yeah, usually tab should work. So if I just have iris $tab,
You type on the top and then it's bottom.
oh, in the bottom left box? You're on control return.
Okay. Oh.
Perfect. You're welcome. Okay, so all right, so we use the column name to get us an entire column of the data. We can now index that object. That is itself an object we can index. However, now that's no longer a data frame, right? That's a one-dimensional column. So we're not going to use matrix notation in terms of row column ways to index it because we only have one column to index. So if we want the 10th entry from the iris $species vector column, then we again use square brackets to index, but here we only type 10, no commas, no blank spaces, and that's it. So iris $species square brackets 10 command or control return, and what's printed is the name of the species in the 10th row of that column or vector. Okay. Maybe you're tired of just printing either one entry or an entire row or column, but you want to print more than one row from this vector, or more than one column and row from your whole data frame. Maybe you're interested in having 5 rows from there. We do this using what's called the C function or the C command, where this letter C is short for concatenate. And then we also use the colon symbol for listing integers from a starting value to an ending value. So the idea is we're going to print all of the rows from 1 to 10. And we're going to do it from the petal length column. So there's a lot going on here. Let's walk through this. So we type the name of the data we want to index, iris, $sign to get us to the column that we want to index. So petal length, square brackets because we're indexing, and then the C function because I want to index a certain set of data from there, and then parentheses 1:10 because I want rows 1 through 10, all 10 of those. Command or control return, and then now it's printed in the console all the 10 values from rows 1 to 10 from the column for petal length. Alternatively, maybe you want a set of rows. So not just 1 through 10, not just 12 through 15, but you want both. You want 1 through 10 and 12 through 15. Now we use a comma inside of the C command. So we have from before, our previous line, our function, okay, we're going through the iris data frame, the petal length column in rows 1 to 10, but I also want to include rows 12 to 15. Yeah. Command or control return on that line, and now we printed all the entries of that data.
In the
Yes.
previous command with just rows 1 to 10, why do we need the C command?
Fair. You don't technically need the C command.
Just to expand to 12.
Yeah. So the question was, why do you need the C command? For this case, we're doing 1 to 10. As a little misleading, you don't actually, I just thought I'd introduce it then. If we only typed 1 to 10, so 1:10 in the console, hit return, we're given the integer values 1 through 10. And so that's sufficient for doing what we want to do, which is index all those rows 1 to 10. So I can get rid of this C command. And this still works just fine. It doesn't make a difference whether you use the C command or not in that case. But as soon as you want to do rows 1 through 10 and rows 12 through 15, commas outside of the C command are not read the way you would want them to be. Here we have unexpected comma in this statement 1:10 comma. But as soon as I put both of those statements inside of the C command, then it works. We have the integers 1 through 15 skipping 11, and then we can use those to index. Yes. Okay. Do we have negative indexing here? We don't. We'll say it now since we're here anyways. We can also negative index, which means print. No. I think we come back to that later. I don't want to jump into it now because I might. Yeah. Moving on. Sorry. Part 5, mathematical operations. So. No. Are there any questions? We're changing gears. Sorry. Before we move on to indexing, are there questions from folks about indexing or reading and viewing data frames? Any orange things on the screen? No orange things on the screen. Okay. We're on time. We're just over 1 hour in. Which page are we on here? We're on math. Oh, we'll keep going. We'll take a break just before we start plotting. Perfect. Okay, mathematical operations. We can use just like a simple calculator to perform basic mathematical operations on numbers. The operators for addition, subtraction, multiplication, and division are what you probably would have guessed: the plus sign, the minus sign, the closest thing we can get to multiplication that's not the letter X, which is the asterisk, and I always get back and forth slash, the slash that starts in the upper right and goes to the bottom left. Anyone actually knows that, a back or forward slash? Let's agree on what we call that from this point forward. Forward slash, great, thank you. This is a forward slash. Great. For exponents, you can exponentiate 2 ways. One is using the caret symbol, the little hat, or you can use a multiplication symbol twice. Either's fine. I don't think there's a difference in speed or anything, and they're both as accurate. So here's quick examples. I'm just going to press Command Return for each of these lines. Each time I do it, the cursor is going to automatically advance to the next line, so I don't have to press the arrow keys. 2 plus 3, we get 5. It ran 2 plus 3. All right, spaces here also don't matter. You can put as many spaces in as you like, or we'll read it. 2 minus 3, you get -1. 2 divided by 3, we get 2/3. 2 cubed for 8, and 2 cubed with the other approach, and we again also get 8. We can use the assignment operator again, if we want, to define a variable, and we can do math on the variable. All right, so we could use the letter A, and we're going to assign the value of 2 to the letter A. So Command Return. And now, in my environment, we see in addition to our two different data sets, we also have a value, a equals 2. And so now we can do our mathematical operations on the variable a representing the value 2, and we should still get all of the same output as before. So a, or 2, plus 3 gives me 5. A minus 3 is minus 1. A times 2 is 6. A divided by 3 is 2/3. A to the third power is 8. We could define another variable, say b, assign it equal to the value of 3. Come on, return. Now I have another value in the environment, b equal to 3. And now we can do math. We can do math on our... we can do all kinds of math on our variables. We're going to do math on the variable a with the value 3 and assign the output of this statement, a minus 3. We're going to assign that to yet another variable, the letter c. So we have c is minus 1, which should be from what a is, which is 2, minus 3. We could assign the output of a times c. Okay, a is 2, c is minus 1, so that should be minus 2. We can assign that output to the variable d. Great. D is equal to minus 2 in our environment. What version did I send you guys? That's fine. Why there's yeah, we're not running those. That's getting ahead. That's left over. I apologize. Okay. Any questions on the basic mathematical operations? Yes.
Does it have log?
Does it have log? Yes, we don't need to load any packages for the basic functions. Thanks. Let's add this here so they act like notes. We have basic functions. Sign, let's see, let's do log. You asked about log. Log is here. You can do log of 5. Command return, we get output. There's always a good question. Which log is this? Is this the natural log or is this the base 10 log? Let's try. We'll do log of 10 and we get 2.3, which means log function as written is the natural log function. If you want log base 10, the convenient way is to type log 10 and you're not using the log base 10 function. And to verify, we'll do log 10 of the value 10 and we get the output of 1. We have more functions, exp for e to the power of whatever value you like. We'll try 1, and we're printed out the value of the constant e. Yeah, pi, the lowercase letters pi is saved forever permanently as a value of pi, the irrational, transcendental. So we also have sine functions, trigonometric functions, sine, cosine. Yeah. Oh, that's fun. Okay, let's talk about that real quick. Okay, so trig, cosine of pi is -1. Sine of pi means it should be 0, right? When I ran sine of pi in the console, I'll do it again so it's our fresh output. What did I get in the output? Is this 0 or not? Okay, it doesn't look like 0, right? This is 1.2 some values times 10 to the -16. This is effectively 0. Computers don't always do things the way that we would think they would do because they have to, right? Sine is actually a polynomial function of many terms stored in R. And so when you run it, it runs that polynomial function. So it'll never give you exactly 0. It'll give you something that's extremely close to 0, such that it's effectively 0. In this instance, really, this value should be considered 0 as 10 to the -16. So there may be cases where you think, oh, my output wasn't 0 as I might have thought. It should be checked to make sure that if it's in scientific notation and with a really big minus sign value. It's just numerical methods output. We might revisit that if there's time to add some later another day, this idea. Okay, so part 6, object types or classes. And then after this, I believe we take a break. So Okay, you may notice that with the commands, when we're indexing iris, petal width, brackets 10, iris species, brackets 10, you get different results. And I see there's a, okay. So let's try iris, petal 10, indexed by the value 10. We just get the value 0.1. We do this with species. We have, okay, the value, setosa. We also have something levels, colon, and then the names of the other types of species in that column vector. What's happening is that these are different types of data. What's being returned. They're different objects or classes, we call them in R. The value returned from the petal width column, the numerical value, whereas the value returned from the species column was both the name of that species, but also the list of all the other species that are present. I'm repeating myself. So those are two examples. What are all of the different types of data that we have in R? Or at least the main ones we'll be working with. There are integers. Yeah, okay, here are the names. Integers, numerics, characters, data frames, which are fancy matrices. There's also just non-fancy matrices. They don't have the column names and the row names, for example. And then there's logicals, or Booleans, and factors. Okay, so other than factors, and for the most part data frames, all of these classes are pretty universal across all programming languages. Factors are specific to R. Python has something that's similar. There's dictionaries, but they're still quite different. And enough said. So examples of these integers. What are the integers? Are rounded counting numbers. So from minus infinity to positive infinity, they're all the counting integers you would have. So in this example, -6, -5, -4, -3, all the way up to positive 4, 5, 6, including 0. These are great for indexing. We use the integers for indexing. Numerics are all the non-rounded numbers, right? So everything in between the rounded numbers, they have decimal points. Typically, your measured data is going to be numerics. Okay, characters. These are also, you can think of these as your strings, if you have some background in programming at all. These are collections of alphanumeric letters, characters, as well as punctuation marks. They're always surrounded by quotation marks. So these could be words, string, cheese, incident. They could just be gobbledygook. They could be names with periods and spaces, like J.K. Rowling. And capitalization is differentiated. So if you use capital letters for one and non-capital letters for the other, those will be recognized as different things. Data frames, those are what we've been working with for analyzing data. The logicals, or the Booleans. These are these statements of truth or falseness, denoted by the all caps letters true, or just the capital T for true. And for false, it's the word in all caps false, or just capital F. These collections of letters, they're reserved because we use the idea of true and false so much in programming. So for example, when we're typing true in all caps, and as soon as I type the E, you'll notice all those letters just changed color because RStudio recognized that I just typed the true statement and that I might do something with it for using logic. And same with my return. Yeah, I get the true statement in response. We'll use these a lot more later on. I'll just say this for now, though. You can use just capital T. It's also recognized for true. Same with false. You can use the whole word false or just F for false. Do it down here. The difference between the characters T and F when they're capitalized is really small and nuanced, and it's easy to maybe mix up whether you typed T or F when you meant F or T if you're just typing those letters. It can be convenient if you want to keep your code short and whatever, but when you start troubleshooting your code, it might be conducive to be writing the whole word because it makes it really clear that you typed true, not F, or you typed false, not T. So it's a quick caveat to throw out there. Where are some examples where true-false statements show up? Suppose you wanted to compare the values of 2 and 5 using the less than sign. So you can type 2 less than 5, which is basically you're asking right now, you're asking R, is 2 less than 5? Humans in the room, is 2 less than 5? Yes, so it's true, 2 is less than 5. So when we type command return, 2 less than 5 is what goes into R, and what comes out is a statement true. 2 is less than 5. If we try 5 less than 2, on the other hand, we should get false, which we do. We get false as a return. So there's a quick example. There are many more we'll come through where you use true and false to compare values that maybe as you're going through your data, you want to only analyze all the values up to a certain value of 5. And so you use these true false statements to help you toggle between which values you analyze and which ones you don't. Yeah, exactly. Useful for indexing some kind of condition on your data. We'll get there soon. Okay, factors. Come back to factors. Yes, factors are vectors or columns of repeating characters or integers. They don't have to be words, they can be numbers also. Repeating characters or integers that are used to subdivide larger collections of other classes into common or shared factors. The word factor is used to make you think about mathematics, right? When you have a big algebraic equation, and there's all these x cubed terms and x squared terms and x terms, and you can factor out all the common x's from there. You can use the factor function, factor classes in a similar way. For example, the species column in our data is defined as a factor because even though there are many different flower entries in the data frame, many of them have the same type of species, one of those 3 different types. So the factor class can be, it can be difficult and awkward conceptually, but it's also very powerful. Maybe you want to analyze those different species groups, so you factor them by the species group. So you want to make a trend line for all the versicolors, a trend line for all the setosas, a trend line for all the virginicas, because they've been factored in those groups. It's really easy to subset the data by those different groups. Yes?
Is it like case sensitive in case some
Yes. Yep. Absolutely. Okay. And then finally, right, we just say words. Yeah, we'll get some more practice with the factors in the future. Instead, I want to jump to talking about vectors and lists. Yeah, okay. So, but I see there might be a question. No, okay. Finally, there are vectors and lists. These are one-dimensional collections of objects that are either all of the same class. So a vector is going to be a one-dimensional object where everything inside the vector is all the same class. Or if they're different classes, then you put them inside of a list. Because of this, lists are typically a little more complicated, while vectors are simpler. The data frame, iris.data, is technically a collection of column vectors, each with a different class, or potentially with different classes. But the data frames aren't recognized as lists. They're given more structure as if it's a matrix. So to find out the class of an object, you can use the class command. We'll practice this on the iris data frame and some of its columns. So if we type class with iris on the inside, command return tells us that's a data frame. If we type class with iris $species on the inside, command return tells us that's a factor. And if you type class with petal width on the inside, it tells us that's a numeric class. Okay, so we're going to return back to vectors and lists to highlight the differences between them in terms of what we can put in them and how we index them. So to define a vector, we use the C function. Again, short for concatenate. So I'm going to call this a.vec for just a quick, easy name so we know what it is. It's a vector and it's got some name, A. This is the convention I use when I define variables. It will happen a lot throughout the rest of this course. You are free to adopt and use any convention you want when you name your variables. This is just the one that I like. So a.vec is assigned the values of 1, 2, 3, and 4. Command return Great, so now in the environment I have, in addition to all the single value variables before, I now have the a.vector variable as well. And it tells me it's a numeric class, 1 to 4 rows, and it has entries 1, 2, 3, 4. Remember, you can't mix up the classes of the objects inside your vector, otherwise R will try to coerce everything to one class only. So a bad vector will be assigned the values 1, 2, 3, 4, and the character string cheese. So command return. Okay, R didn't throw an error, right, in the console. A bad vec was defined. We go and look at, quickly we see in the environment, all the values 1, 2, 3, 4 have quotes around them. If I type the name of this vector, I can have it and execute the name. So a.bad.vec, I'm typing down in the console, and I press command return. Then what are printed are all the entries in a bad vec, and we see that all the numbers 1, 2, 3, 4 have been written in quotes. So basically, because there were some numerics and a character inside of this one vector, RStudio said, well, it's easier for me to convert all of these numerics into characters than it is for me to convert cheese into numbers, because I don't know how to convert cheese into numbers. So it just made everything a character instead. Okay, but maybe you actually want to keep the classes mixed, in which case we use a list and the list function. So to make a list, we don't use the C function anymore, we use the list function. We still assign it the same way, a.list assigned as list. And inside of this, we type, yes, good. We have the entries 1, 2, 3, 4, name cheese. We're also going to put inside of this list the vector, a vec. We're also put inside of this list the vector, a bad vec. And at the very end, we're going to add to this list our data frame, iris, to really drive home the point. The list can be a mixture of things. You could even put another list inside of this list, which you don't need to do right now. So let's run that. Command or control return on a.list. It's defined up in the data section as opposed to with the values. I don't have a good answer for why. That's how R parses this. But the nice thing about that is that we can click on the little arrow button and it shows us all the different things that are inside of this list. Alternatively, we can just type the name of the list and run that command, a.list, command return, and displayed in the console are all of the things inside that list. Oh, I forgot there's a data frame in here, so I have to scroll way back to get back before the data frame. And here's the other entries in the list. Number 8 is for the iris data frame, 7 is for the a bad vector, 6 is for the a vector, and then 5, 4, 3, 2, 1 is for cheese and values 4, 3, 2, 1. So we should realize what's happened here. When you're defining a vector, every time you put in a comma between your entries, those are like different rows in that single vector. When you're defining a list, every time you have a comma between elements when you define that list, as we do here, these are each being entered in as a wholly separate object inside the list. So the value of 1 and 2 and 3 and 4 as single integers have been each given their own place in this list in the same way that these other vectors have been given their own place in this list. Own place, that's indexing. So we'll index lists and see how this works some more. Indexing lists is different. Oh, yeah. All right, so if maybe we wanted to access the character cheese inside the bad vector, which is the 7th thing inside this list, we need to use 2 indices again, because the first index tells us which object in the list we're talking about, the bad vector, and then the second index tells us which entry in the bad vector we're now talking about. It's almost like 2-dimensional indexing, but slightly different. So, indexing lists. We use double square brackets to index lists to access the first element. So a.list, I want to access the first object here, the number 1 inside of this list, and I type square brackets 1 to get the first object inside a.list. Then I press command return, and it prints for me the value of 1, which is what is stored in that first entry. Or I could do the value 5 to get that single instance of the word cheese. Or we could come here and do 6 to get us that whole vector AVEC, which value is 1, 2, 3, 4. Or the value 7, so we can index the 7th object in a.list, which is the bad vector, which has the characters 1, 2, 3, 4, and the word cheese. But now maybe I want to access the word cheese from this vector in the list, the 7th object in the list, so I need to now index again. So a.list double bracket 7 gets us the bad vector 1, 2, 3, 4 with cheese. If I want the cheese entry from there, I use single square brackets because, right, this is a character vector, so I only need single square brackets. And I type in number 5 because the 5th entry, command or control return, and now I get the word cheese printed back. Okay. Yeah, good. Cool. As I mentioned, indexing is super important, so I promise we will get more practice with indexing all these different objects throughout the next couple of days. Are there any questions about indexing or object types, since that's what this actual section is about? Okay, and if not, let's break for 10 minutes and come back at 11:15, and then we will continue on with making graphs. Cool. Oh boy. How's it going?
Before the working checkup, because like, so here you can run only what you did here, no?
Or we could put whole new things in here too.
Okay.
Like I could type, I could make new vectors down here if I want. G is 1, 2, 3, and that also is fine.
Okay, so then why we use both of this?
Just as with Python. Right, so Simon, typing here, like all this, everything we type up here in the script, we can save as a file, so we can come back to it later, like those .py files we had. And then the console just displays and shows you, oh, this is what you ran, here's the output. It's like when we had the print statements. It's the same idea. Here's what you ran, here's the output you told me to make. Yeah, I like the script because I can save it. Right, it's like working in, well, yeah.
And these outputs, you cannot save them. You just have to print them shot to save.
No, you have to rerun it. Like, so when I close this, I could press Command S, and this file has been saved. I could close RStudio, and then I open it up again. The file, everything I did in the file is still there, but in the console, it's going to be blank. Now, it has a log of your most recent sessions, so you can use the arrow keys and you can go back up to what you ran in the recent sessions, but that only goes so far. So it's not saved permanently. You might save like a few hundred entries temporarily. Yep.
If you have to run everything, then you can run the whole script.
Yep. If nothing happened, I ran the comment, and yeah. So if I wanted to run the whole script, I could run the whole script. I would highlight the whole thing to run the whole script, or I think if you press the source button, it runs the whole thing. Yeah. So the way that RStudio reads scripts is very different from how Spider reads Python scripts, where you had those cells. Right, with R, I can execute code line by line by line, and I don't have to have these giant cells, and it just tabs through as we go.
Hey,
Hi.
thanks for doing this.
Of course.
I actually have a project working on quantitative muscle town.
Oh,
So
cool.
I saw your presentation
Yeah.
of the CT scan. That's awesome.
Right on.
Do you have any like undergrads or grad students that are looking for a project?
We don't. We're actually
No.
looking for undergrads and
Undergrads.
grads who are looking for projects, so we can give them projects to do.
Okay, fair. I thought that might be the case.
Same.
I don't know. Who do you think there's anyone I could talk to just about advice about the project?
I mean, you could talk to us. So as the collaboratory, we sort of offer two services. One
Mhm.
service is the workshop itself, and then the other service is collaboration advice on different projects.
Mhm.
And so if you'd be interested in talking to us, our expertise is in the segmentation and the modeling side.
Mhm.
It's not so much in the biology side.
Mhm. Yeah,
So I don't know where
I don't need help
you
with
guys are
biology
interested.
side.
Oh,
Need
okay.
help with the informatics, yeah.
Yeah, so you could go through the collaboratory webpage. You can like put in like a work order,
Oh, really?
basically. Yeah, or I think you send an email. Collaboratory, of course. You see like let's see, workshops, analysis. Yeah, so I just joined the group, so we're not advertising the image analysis specialized training, but we do have it. Like I mentioned, we focus on vascular segmentation. There's some other folks that do actual like cellular molecular image analysis. And so, but most of the folks here do sequencing analysis. But if you're interested in getting some assistance, you can email the person who runs the collaboratory, Matteo Pellegrini. And I think you just basically give him like a quick explanation of the project and the problems you folks have, what kind of advice you're looking for. And then he tries to match you up with whoever makes the most sense.
Okay, cool.
And yeah, and if it's something that we could help with, either using our software or just providing assistance in terms of you can talk to these folks, or
Okay, that's
I guess
awesome.
how we approach these kinds of problems, we'd be happy to help.
Okay, that's really cool.
Yeah.
Thank you.
Yeah, of course. Yes. Or I can come to you too if it's easier. You can keep your computer there. Leave the two. The two. Just from here. Oh, sorry, no, quotes. It needs to be quotes. Singular double quotes, no quotation marks. For the name of the There's the hierarchy. If they didn't say error, yeah. Oh, but that's the point. I actually want you guys to. It's true. Yeah. Yeah, I try to speak slowly, but you still. Yeah. Hey. Hi. Come on. Nice to meet you.
Yeah, sorry.
No, it's okay.
Stayed all the way across.
Did you drive down just this morning?
Yeah.
Oh, okay, cool.
Yeah,
Nice.
it's just like I stayed in Hollywood.
Oh, yeah.
Insane.
Yeah.
Anyways, how you doing?
It drives me insane. I'm doing well.
It's good.
I'm glad that we're cruising now.
Things
Yeah.
are good. Questions clear.
Yeah. Yeah, that question's been good. And folks, there's been, like, did they have questions about the data sets too in the emails? When folks said they didn't have the R file, it made me think that they might not have had the.
Yeah, people just dragged it in conversation that everyone had it. And that
Oh,
email
okay.
from like one person.
Perfect.
That's good. Yeah.
Cool.
The Zoom's a lot cleaner than the WebEx.
Is it? WebEx was, I don't even actually know. It was tricky. Like it just, like for some reason every day.
Nah,
set up and
Zoom's
running.
killing
It's crazy.
It makes
Cool.
it easy. WebEx is super fun.
Good.
Yeah, that one
That's
good.
good.
Yes, it's great.
serious. With this, your workshop this afternoon.
Yeah.
If we just switch, I mean, is a similar role, is that going to work out? If I just hang out in the back and fill the questions for folks?
Yep.
Cool. Yep. Easy.
Should be plug and play.
Right on. I don't know how many folks in here might be taking the workshop also. I only say that because I'm going to mention some of the statistics functions in R, so that people like know the functions exist and where to find them and a little bit about how to use them, but we're not going to really talk about statistics.
We don't use any of those functions.
Oh, okay, cool. Then yeah, overlap shouldn't matter or anything. But yeah, if folks ask me, because like I don't do ANOVAs, but a lot of people I know do ANOVAs. ANOVA functions not hard, so it's like, well, here it is, we can make some graphs.
Yeah.
But I did this with the big students, and we had some questions that I couldn't answer. Like, you guys have got to talk to your mentors. They can help you. Yeah, I was gonna say, yeah, like we've got more workshop on stats. Here's just where the functions exist.
Yeah.
Cool. Excellent. Oh, are we there? Oh, we're so close.
The class will be until 12 or 12:30?
I thought 12:30, 9:30 to 12:30.
Okay, online it says 12, so I'll have to leave early because I have an appointment at 12.
Really?
Yeah.
Oh, wow. It does say 12 online.
I think this is so I'm at their school for me.
2.5 hours per day.
But
Yeah, that's fine. If that's what it says, that's what we have to do.
I read somewhere that it was 12:30.
It might have been the email I sent because I've been so convinced. I just have to check if this is
usually these books are always 3 hours. So
right. Right. That's why, yeah, because the Python one, which is the one I'm
yeah.
coming from having done, was 3 hours per day. Yeah, 1:30 to 4:30. We go to R,
2.5 hours.
2.5, 9:30 to 12. No. Cool. Okay. We'll be stopping at 12 then. No, it's what we've advertised. Yeah. And I'll figure out the rest from there. Thank you for pointing that out. Cool. Okay, so we're going to start back up again. Someone just pointed out a very important fact about this course that I regrettably overlooked in my planning. Having taught the Python workshop last week, I'd assume that it was, as with Python workshop, a 3-hour workshop each day. But in reality, on our website listing, this course is 3 days. Each day is 2.5 hours per day, and it's very clear at 9:30 noon. So we will be ending it today. Yeah, I know some folks, that's exciting. So if you, the email I sent, I said 9:30 to 12:30, which is why some of you might be thinking, what? I thought you said 12:30. I was, this is fun. So if you're worried about a schedule complication, worry no more. We'll end at noon, and I will sort out our content to try and make this work for the next few days, namely the next 2. We're moving on. I can anticipate, though, that we probably won't have any time today for coding on our own, but that just might mean that we start with that tomorrow instead. Just a quick caveat. So let's push on through to the end for the day. So we're going to start talking about graphing. This section is called basic plotting. It should really be called GG plotting, because the more you learn about the world of R, the more you'll learn that there is an incredibly vibrant conversation about the different ways we can make graphs. There's how much do I say this here? Not at all. Okay, so in R, R has its own, we use the word native, but it's like inherent function for making graphs called plot. You don't have to like install anything from the internet to do it. So you could plot some of your data. I'm just going to do this above because we're not going to really be doing this. You type the function plot, and then you need to enter some X and Y columns that represent the data that you're plotting, and then it makes a graph. And this was the original traditional way of making graphs in R. Some folks weren't very happy with how clunky that way of plotting works. So they made a new package, a new library called ggplot. And so I renamed this section because if you were to Google these phrases, if you want to Google a question about the basic plot function, then you typically Google something like basic plotting R. And then that gives you all of the hits and responses for the original basic plotting functionality in R. But we're going to work on with what's called ggplotting, which is the sort of new way of how to make graphs in R. Depending on who you ask, people might have extremely opinionated stances about which one is better or worse, and for very different reasons. I tend to use whichever one I can find a good example of online, and that fits my needs. And so my code actually has mixtures of ggplotting and basic plotting mixed in. But I appreciate the, we'll be using ggplotting throughout here. So we use one consistent one. And I'm doing that because I feel like to make graphs in ggplot, it's a little, at first, the learning curve is steep, it's less intuitive. So we're going to do that one. Also, they're very pretty. Whereas basic plotting, you have to do a lot of work to make them pretty off the bat. So, there's questions. I wonder if I stirred the pot of the debate. However, ggplot is not inherently in R. We have to download it from the internet. It's a package. Packages are extra bundles of functions and utilities that don't come with your default installation. You likely don't already have ggplot unless you've been running code in advance, which is fine. So the first thing we'll do is run the function install.packages with the argument, in quotes, ggplot2. And that should, for me, it looks like it's trying to update my ggplot package. For you folks, it should be going through similar looking streams of output as RStudio goes into the internet and finds the website where the library is held and downloads it and then opens up and installs it and stores it in your computer. Just make so we should all run that line of code install.packages ggplot2, so we all have ggplot installed. Yes. Yes and no. Yes, in that there are some organizational offerings of examples of how to use ggplot, and I'll try and show those at the end of the websites for. I think it's like StatDH or StatEDH or something. And it's very nice because they basically have these brief tutorials for all the different kinds of ggplot graphs you want to make. So you go find the graph you want to make, and then it provides you with simple code for how to do it. But of course, once you start trying to do fairly advanced things with that code, now you have to start looking for some other examples, possibly, if you can't sort it out on your own. And then that problem's kind of inevitable. When you go online and look for example code from someone else, it may be really good, it may be really bad. We'll have an activity where we look at some examples to try and help identify what good versus bad example code looks like. Yeah, okay, right now, loading the library. Once you've installed the package, you need to use the library function with the package name to load it into our active workspace. This had been previously, you just type library ggplot2, command return. On the Mac, it seems fine. Someone, you are on a Mac, we having problems also. If that's not working, you could try putting it in quotes. Ooh, why did that happen? There. Nope, that's installed. Here. You could try putting ggplot2 in quotes inside this call to the library function. It didn't have the same output. Yeah. Okay. As soon as we're willing to run this function, so we all have ggplot actively opened and running on RStudio. Now, this is confusing to use ggplot. We're going to be typing just the phrase ggplot often, even though the library is called ggplot2. I don't know why the library is called ggplot2 and the functions is ggplot, other than something about version control and someone decided to call it ggplot2. Okay. Right, default plotting, favored. Oh, there's a commentary. Okay, we're going to go straight to histograms of data. Okay, some of how this okay, many of you have made graphs before, so please don't feel like I'm speaking down to you in the room as I introduce different types of graphs. For some of you, these might be new graphs, which is great. If you're familiar with all of these, that's also excellent. At least now maybe you'll become familiar with how to run them in R. Yes, quick question.
Have you ever got an error message that ggplot was built under our version 3.5.3, some other version?
Yes, I have.
Does that mean ggplot's deprecated, or?
I want to say yes to that question. I'm not sure. When you say deprecated, I don't know.
Like, does it still work with current version?
Yes. Yeah, so it should still be working. Yeah, so sometimes these packages, you'll get these warnings, say, warning or caution, this version you're using or the version that exists was made, you know, this is the version number it works with, or it was made for this version of R. That's a warning that's not telling you it's not going to work at all. You just might have some interference between different packages that were made with different times for different versions of R itself. ggplot should run fine on everyone's computer. That shouldn't be an issue. It's deprecated. But that can happen. It's usually more with like very special packages that someone made just for their own purpose, and you happen to be one of 5 other people in the world who wants to use it, and they made it like 10 years ago. That's when that error message becomes a little more salient. Yeah, thanks. That's a good question, because that is a common message, and it's not a big concern. Right. So the graphs. Right. So as I mentioned, the structure of the workshop is we're going to now explore more R functionality through like a data sciencey kind of approach. We're going to make some graphs, ask questions about the data in the graphs to help guide things we're going to try and do that allow us to explore new aspects of R. But again, basically, please don't be offended if you feel like I'm over-explaining different types of graphs. Okay, right, histogram, common plot, plots the frequencies that data appears within certain ranges of values or within certain bins. So we're gonna make a basic histogram with ggplot. First, you have to tell R which data set we want to graph using ggplot and which aspect of the data in particular we want to graph, which column, for example. The AES function, which will go inside of the ggplot function, we're gonna do functions inside of functions. It's gonna be strange, but we'll walk through it. The AES function refers to the aesthetics of the graph, and it's how we tell R specifically which data to plot, and in this case, to associate the petal length values with the x-axis of the histogram. The plus symbol tells R, good, here's an example. The plus symbol that shows up in these ggplot commands tells R that we're going to do more in the following line. It's like, don't finish running yet, more code is coming. And in this case, that's where we tell R that we're going to make a histogram out of the data. It also is a nice way to allow you to automatically format and structure your plot commands so that you can say, oh, this is where I define the x-axis variable. Oh, this is where I specify the labels and the tick marks and their locations. And this is where I build the legend. Like it gives you all this nice road structure in building the plots. So let's make our first plot. We call the ggplot function. Looks like the basic plot function, but it has 2 G's at the beginning, open parentheses. And then, right, let's do this as if for the first time. A lot of this stuff comes with tab completion too. So if I type ggplot and then type tab, the first thing that shows up is data. What is the data you want us to make a graph out of? Well, we're gonna use the iris data set. And then AES, when you get tab completion for aesthetics, and we open parentheses, and now we can start specifying information about which column we want to make the graph of in this plot. So I'll get rid of this example line. Okay, so we have our function called a ggplot. We tell it the data we're going to use is the iris data set. For the aesthetics, the x-axis is going to be the, okay, sepal width column, but we have to specify this as a point. close parentheses for AAS, close parentheses for ggplot, plus sign because we want to do more, return, and here we type geom histogram. There's an underscore between the two, and then in parentheses we have bins equals 10. So in the ggplot world, there are many functions that start with geom. It stands for like geometric object. We want to make a geometric object. It is a histogram graph out of the data. So you'll often see geom underscore something. In this case, the thing is the histogram. And then here, we get to specify the number of bins we're going to use for the data. So we're going to take all the data along the x-axis. We're going to make 10 bins from the minimum to the maximum values, evenly distributed bins, and then see how many times different data points fall within each of those 10 bins to make our histogram. Except we're not doing it. RStudio does it. I press Command Return. Nothing happened. Oh no. Oh, why? Because the window for my plots come out I made so small. So let's try it again. I'll run the code a second time, run both lines, and now our plot has been rendered in the bottom right. Okay. So here's a histogram of the data. Again, supple width going to the right. You could count about 10 of these step jumps for the 10 different bins. The vertical axis is count or frequency of observations for each bin. And then the ggplot, so this is part of the reason why people like it in some ways. It automatically has kind of this nice or pretty formatting. You'll notice that we've got major and minor grid lines in the background with this sort of soft gray hue to help us identify what's the background of the graph, what's the data in the graph, and then where are the grid lines showing up. But we're going to learn how to modify all of this to make publication level graphs. So great, but that is a rather messy graph. Let's add some change. Let's change the bin width and the bin color. Maybe we don't want gray on gray. Maybe we want something else. So this is where it starts getting into the other nice aspects of ggplot. We're going to keep everything we have. The data set we're plotting is iris. The x-axis is supple width. We're making histograms. We're using 10 bins. Sorry. There, good. 10 bins, but change the color. We use what's called the fill parameter or the fill argument inside of the geom histogram function call. We're going to change it to green. Green is a recognized character in R as the color green, in quotes, lowercase. And we just call it fill because we're filling the bins with the color of green. So command return on that line of code. Oh, I know what's happening. Sorry, I get it. What did I do? I put my cursor only on the second line for geom histogram. I hit command return, and I got an error, nothing came out. Oh, sorry, no error, just nothing came out. You have to run both lines of code, so you can either highlight both lines and return on those, or you could leave the cursor on the first line and press command return twice, and then ggplot will run everything correctly. Oh, that's good. On your screens, it's probably a really bright, hideous neon green color. On the projector, it's a nice, nice subdued green. Okay. Which is why I say here, oh, the comments. That's why I say here it's not exactly better, but you see we can adjust the boundary color and the fill color for the bins. How about the bin width? We're doing bins. Okay, bin width is done by number of bins. So to do that, again, we just change the number that we have next to the bins. Here we're doing a couple of silly examples to just drive home some points in case histograms are new to you. One thing you have to do is decide on the number of bins to use in your histograms. If you use too many, so here you have 100 bins, then our data is pretty discontinuous because there's a lot of areas here where there's no data, so the bins just drop down to 0. And if we kept on going using more and more and more bins, then eventually we'd reach a point where every data point gets its own bin, and we have a very boring distribution we can't learn much from. If we put everything inside of one bin, then we just get one gigantic rectangle, which is also extremely uninformative.
And so yes, there is like an ideal area in between too many and too few. Some people say there is an art to it. Some people say it depends on if your distribution is normal or not. Then you can use, I think it's the cube root of the number of data points you have. Ideally, you just want to make sure you're capturing the interesting features in your distribution in making your histograms. So that's why it's nice to just be able to really quickly change the number of bins here, though, so you can explore that information. Right. So here's a good example. We go between 10 and 20. I keep forgetting to use both lines. So 10, this looks like it's okay. I guess you could say a very sure, roughly normal looking distribution. But when we jump to 20 bins, we start to resolve a little more of the internal structure in the distribution. We see we have multiple peaks in different areas. Oh, we're looking at the width of leaves of flowers for 3 different species of flower. Maybe that has to do with the fact that there's different species, who knows? We'll come back to that. But this highlights some of the advantages of being able to quickly specify bin number. You can explore your data some. All right, well, let's just keep pretending like it's all one species. Keep it all the same color. Let's do some rudimentary statistics by calculating the mean value of the width and adding its value to the graph as a visual line. So first we'll learn to use the mean function. The mean function, to calculate the mean, is just called mean. It's a very aptly named function. Open parentheses. When you're typing this function, it's going to say x equals, and then you provide it with the name of the vector of data you want to calculate the mean value for. Some of you, your data might have NA values inside, in which case you use the parameter NA.rm for remove NAs from the distribution. You don't have to go through the data and remove them yourself. You can just use this parameter inside the function and it'll remove them for you by saying true. NA.rm equals true. So command return on that call the mean function, and our runs and prints the value 3.0573, which is sure roughly where the center of this larger, broader distribution is. But if we want to use that number and do something with it in the graph, we need to assign its value to a variable so we can call the variable name later. So I'm going to make a new variable called mean.sep.width for mean sepal width. And it'll be equal to the mean value of the iris sepal width column. So now we can scroll down in our environment and see in the value section we should have good mean.sep ... more name and then the value. So how do we add this line to the graph? We use from before our ggplot function call, data is iris, AES aesthetics is sepal width, plus the fact that we want to add histogram to make the graph out of, plus we want to add a vertical line. So now we use the geom, geometric, vertical line, v-line function. And here we have to change the aesthetics because we're not, this isn't going to be using the sepal width information. We're going to just put in here, right? So a lot of this is autocomplete stuff. So let's see the example. We could type geom underscore tab complete. Oh, there's an AB line if we wanted. Here we go. Many options. AB line, area, bar chart, blank box plot, blah, blah, blah. Vertical line, V line. And then aesthetics. It's not showing up, that's fine. The x-intercept for this will be the mean sepal width value. That's fine, okay. So I'll highlight all 3 lines of code, press command return, and now we have in our graph the same histogram as before in gray, and in black as the default color for the vertical line, a vertical line located right where the mean value is. Let's see. We can change some of the formatting of this line though, so we can make it maybe easier to see, maybe not a solid line. So again, using all the same values from the same lines of code we ran before, outside of the aesthetics command, but before we finish the geomv line command, we have a comma, because now we're going to add some parameters to change the values in this graph. So first, we're going to change the color to make it blue. We're going to change the line type as another parameter. So it's no longer a solid line, but it's a dashed line. And we're going to change the size, the thickness of this line, using a value of 1. And that's a multiplier. I forget what it's based in terms of, but it's like a scaling multiplicative factor for the size or the thickness of the line. And it's easy to experiment with if you want to try different values. So highlight these lines of code, press Command Return, and now we should have same as before, but now it's a nice, hopefully more visible, folks in the back, dashed blue line at that same location. Okay. Where are we going? Oh, that's right.
For why do you,
Oh, sure.
a little clarification on why you do the na.rm equals t.
Okay. Why na.rm equals t? So sometimes in your data, you might have na values. We don't in this case. We could make it so. No, let's not do that. Let's just make a new test vector, something with values 1 to 10, and an NA value, and maybe an NA value also, and then 12 to 100. So now there's this test vector that has a bunch of values as well as an NA and an NAN entry. Sometimes when you record data, you have missing values in your data. When you run the mean function on this vector that has NA values in it, it gives you an NA because it cannot compute with NA values. But if you would like to calculate the mean of that vector without having to go inside and remove those values or index everything but those values, you can just type na.rm equals t or true, which means we will remove, that's the rm, all of the NAs, that's the NA, from the vector, and then calculate the mean. Great. That worked. So that's the Don is taking on the representation of all people online as I look at you now to say that's the reason why we have the na.rm equals true. Excellent. Glad we could cover it. Okay. Let's look at some more ways to cut our data and make some fun graphs. Now a question. Oh, I know why. That's when there's no blanks, I lose my place. How many bins is right? We did that. Add a mean bar. We did that. Change some formatting. We did that. Now a question. Our data has values for 3 different groups. We've plotted all of them together in one histogram. Which species is this mean value of sepal lengths for? Setosa, versicolor, virginicolor, some combination of them, all of them? It's for all of them. So maybe we should split our data by the species and try plotting each separately by color, but in the same graph. This is where the factor class comes in handy. We're going to factor the data by the species and basically make a graph for each of the factors that we have. And the nice thing is having a whole type of object or class reserved for this means that a lot of the functionality in R is designed to automatically do things if you have factors. So we don't have to really type any new code. So for example, this is the big difference between the previous instance and the new one. We have the same thing as before. We have ggplot, data's iris, aesthetics or sepal width, the call to the histogram, the call to the vertical line, and then we modify the line type. Let's talk and read at the same time. Found you. But if we want to color the histogram data by species, then we can go inside of the aesthetics for the histogram, the main ggplot command. So here we have x equals sepal width, a comma, fill equals the name of the factor column, species, that we want to factor the data by. So let's see what happens when we run this line of code now. First command, return all 4. Oh, how cool. So we've basically taken our data set and we said, okay, we want to use the iris data. We want to make our aesthetics based on the width. We're going to be plotting the width. And we're going to be coloring by the species factor. So R basically took that whole data set, and you can imagine it sort of subset by the species and then made a different colored histogram for each of those species. Since we didn't tell it what colors to use, it assumed some colors. It chose blue, red, green, and then also chose a formatting style for how to plot the histograms next to each other. For example, it looks like our values are stacked on top of one another. Right, so it did blue first, and then it plotted green and put green on top, and then it plotted red and put red on top of green on top of blue. Maybe that's your style. Maybe that's the journal you're submitted to wants histograms done that way. Maybe it doesn't. Maybe you want them side by side. It's really easy to change that. We use what's called the Dodge parameter. So now you can put your histograms, sorry, they all start on the y = 0 line as opposed to being stacked. Yeah, fine, good. So to do that inside the histogram call, where we specify the number of bins, then we add a parameter which is position equals identity, and alpha equals 0.5. Right, if all of these histograms start from the same vertical line, that means they're going to be overlapping each other. And so we want to make them transparent so we can see through the different layers and see all the different histograms that are present. The position equals identity forces all the histograms to be at the same vertical line for where they start, and alpha equals 0.5 modifies the transparency. If alpha is 0, I believe it's 100% transparent, which means I think you can't see it. And if alpha equals 1, it's 100% opaque, 0 transparency. 0.5 is a great middle ground. Oh, don't highlight everything. Okay, so we'll highlight these lines of code, press Command Return, and now, yes, good. All 3 of those histograms start at the same vertical line, and they're slightly transparent so you can see through to see roughly where it doesn't show up quite as nicely on this one here. The blue to green to red, here you can see transparently a little bit where the color shifts. There was, that's getting ahead. There was also, I think if we use Dodge instead, that gets us side by side. Yes, okay, so an alternative entry for the position parameter is the statement Dodge. Right, so before we had identity, position equals identity, not identify, identity. And identity, when you run that, we have everything starting from the same horizontal line and slightly transparent. If you use position equals Dodge, there's no overlap now. Now the bins are placed side by side. So we can, I ran that previously. Run it if you haven't yet. Here is what it looks like when you run it. Since they're side by side, we don't need transparency. So we'll remove the alpha parameter because if there's unnecessary transparency, then things just tend to look transparent. So now they're not transparent. They're Dodge, they're side by side, but a quick warning, if you're doing histograms of continuous data like this and you're using the the Dodge parameter, then it gets a little confusing to read this x-axis variable because now, right, they've grouped them in triplets. So we have, for every one of the 20 bins, we have a red bin, green bin, blue bin that corresponds to the first of the 20 bin values. And then we jump to the next value for our next triplet of bins, triplet of bins, triplet of bins. So like reading the values of those continuous axes gets kind of confusing. There's a trade-off, I guess. We'll find there's always a trade-off. Okay. Let's go back to the identity setup. So, okay, clearly this mean value for petal length doesn't well represent the different species. So we're going to add mean values for each of the different species instead. However, we have a problem. We didn't yet calculate the mean value for each of the species. We've only calculated the mean value for all of them.
So now we're going to practice indexing using logicals. So we want to extract all of the rows of the iris data frame whose species value is either Setosa, versicolor, or virginica. We can do this by writing a logical statement comparing every value in the species vector with the name of interest. There's a lot to unpack. We're going to do this chunk by chunk. We're going to build up a function call for this. And this is great. We will end on time. So what happens if I write the command iris $ species double equals quotes Setosa? What does double equals mean in the first place? Quick example, double equals of 2 and 5. 2 double equals 5. That is asking R the question, is 2 exactly equal to 5? It is not. And so R returns a value false. Or I could try words. Is the word good exactly equal to the word bad? No. They're different characters. Good is good, bad is bad. So we're going to use that type of logical comparison for the species names. So here we have on the left, iris $ species just means look at all of the species we have in that column, their names. Double equals means compare every single one of them to the name Setosa. So if I run this whole single line, I should get 150 true and false statements where the trues correspond to the entries of the species column where the name is exactly spelled as Setosa, and the falses are for everything else. And if I do this for the next 2 lines, for the other 2 species names, virginica and versicolor, then where these true groupings occur, changes correspondingly for that column. So, great. We can do this comparison between the names to get these true, false returns, these outputs. Now we're going to use the which function, new function. This which function tells you the row index value that corresponds to your true statements, and it ignores the falses. So we're going to put inside the which function this iris $ species equals Setosa, and it should return all of the index values for the rows that correspond to the true values for the iris $ species equals Setosa code. And the same for the versicolor and virginica scenarios. So for each of these, we get the, so okay, conveniently this data is broken up into thirds. The first 50 rows are all Setosa, the next 50 are all versicolor, and the final 50 are all virginica. Now that we have the indices at hand, we can index with them to access values. All right, so now we can use this vector of indices to subset petal width column vector to extract petal length values. Sorry, that should say sepal width values. Couldn't decide which column to use. So we're going to extract the sepal width values that correspond to those 3 different species one at a time. So now we take from before that which function with iris $ species equals Setosa, parentheses, and we're going to put that inside of an index call for the iris $ sepal width column. And one thing why we're doing it this way is one, because right, these are large chunks of code to parse, but 2, it also helps us. I want to sort of demonstrate to you a way you can troubleshoot these kinds of lines of code that you might type when you're doing such indexing practices. If you're confused ever by what one single line of code means, they're like onions, right? They have layers. You can go straight to the center and say, okay, what does this part at the very center do? So I'm going to go into all the parentheses I can find, and find iris species equals Setosa, and then you can just run that part that you highlight and say, oh, that's a logical comparison. That's looking at all the names in this column and comparing it to this name here. And then you can go to the next layer and see what does that part of the code do. That gives me all the indices for the trues. The next part of the code, oh, okay, I use those indices to get the sepal width values corresponding to those indices, corresponding to the Setosa species. Okay. But the same thing, it works for the next 2 as well. For the versicolor and virginica, we get the values corresponding to sepal widths for each of those species.
So as before, since we want to make a vertical bar that represents the mean value for each of them, we need to assign the value of the mean output to 3 different variable names. So in this next block here, we've defined new variables called AVE for average, setosa, sepal width, and it's assigned the value from the mean function. And so inside the mean function, there's the iris sepal width indexed by the which function, where we compare all the species names to the setosa name. So now the average sepal width, average setosa sepal width has a value of 3.428. And the same thing for the versicolor and virginica. Notice we changed the names just slightly to keep track of the different species that we're calculating the average values for. So here's for versicolor, here's for virginica. Okay. That's coercion. We don't need that. We'll come back. We don't talk about coercion today, so we'll get back to that later. That's what do you do when you want to factor something that's not a factor? You use a factor function, but we'll returning later. Okay. So, unfortunately, the way ggplot works, you have to make data frames out of everything to read into. So to keep things tidy, what we're going to do is we're going to define a new data frame that's just for these mean values. So we have this, we're going to assign to the variable name means a new data frame. And inside this called the data frame, we're going to name the first column, in quotes, mean values. And the values are using the concatenate function, the C function. The names of these are the variables: average setosa sepal width, average versicolor sepal width, average virginica sepal width. And then in the next column of this data frame, we're going to have a species name column. And it's really important that I give this column of species names the same name as what shows up in the iris data set that we feed into the ggplot function. Because what ggplot's going to do is it's going to match these different data frames and say, oh, your data is coming from this data frame iris, and you have these species column here, and you're given to this other data frame of mean values, but we also want to be able to break them apart by species. So we need another species column name spelled the exact same way to go across the 2 data frames. So we can define this means column. We can click on it from the environment and view it. So great, here's the mean values column, here's the species column, and I spelled species, capital S, lowercase species, same as it shows up in iris data frame, capital S, lowercase species, and the ordering is also the same, setosa, versicolor, virginica, and the same with iris data set, setosa, versicolor, virginica. Yeah, good. Now we're ready to roll. We can use one call to the geom vertical line function to add lines for each mean value, instead of having to add a geom vline function for each of the lines, right? So by making this other data frame, we use one function once instead of one function 3 times. So in this instance, when we define geom vline, we make a new call to data and say data equals the means table. And in the aesthetics, we tell it that the x-intercept will be the mean values column from that data frame. And we're going to color by species, the species column. And then outside of the aesthetics, here's where we specify things that are going to be true for all of the lines. All right, so inside the aesthetics are parameters we want to be specific by species. Outside of aesthetics are parameters we want to be specific to all of the data. So the line type will all be dashed. The size will be 1. Let's run this whole block. Command return. Oh, terrific. We now have, in addition to our 3 colored histograms from before, we have 3 vertical lines with matching colors. They're all dashed. They're all the same size, but they're located where the corresponding mean values are for each of those smaller distributions. If we wanted to specify a different line type for each species, we'd remove this line type equals dash function call from outside of aesthetics. We'd put it inside of aesthetics, And then we could either just say line type equals species, you figure it out R, pick the 3 most common line types you like, or, well, yeah, let's just do that. Let's see what happens. Run. R picked, okay, it picked solid line for the first one, dash line for the second, and a high frequency dash for the third. Or instead we could have, if we wanted to specify it specifically, we use the C function and type in words. I think solid is what the first one is, dashed, dot, dashed. These aren't things that commit to memory. I just Google them, so we'll find out if that works. It worked, great. Oh, and it made a second legend for us over here. That's great. That's convenient. But so yeah, so there's 2 examples to demonstrate how to break up your data and plot by different groups in your factor. 3 minutes. 3 minutes to show you where the t-tests are. No, absolutely not. Okay, so we're going to end for the day. But first, sorry, are there any questions on what we've done so far in terms of this splitting, factoring your data, making graphs for each one? No, all right. In that case, we're done. You already have a master's copy of the worksheets, so I won't need to send you anything for that. But I will send you material that we'll be using for tomorrow as soon as we finish today's worksheet, where we pick up with the same data set, but we'll look into t-tests and modifying legends. And sorry, we didn't have any time for breakout coding today, but hopefully that'll be better by tomorrow. And that's it. Way to go. Day 1, chat. Oh, yes.
Look at that last bit of code you wrote again.
Of course.
That's not in the.
This one.
That one, yeah, the one where the lines were all different.
Oh, yeah, of course. Let's see, the one that was here. This is the one that was here. Should be the one that you have. Oh, why did I do it that way? And then if you want to make, so here I can say, for all with same line type. Oh, thank you very much. For different line types by species, we move the line type parameter from outside the aesthetics AES function to inside. So it follows just after the, oh no, here. Just after color equals species, we type line type equals also species. If you don't care what type of lines are used for each case. Kind of. Sure.
I don't see this iris data.
Oh yeah, so I didn't want to get into what was happening with that, so that's why I just put a comment on it and then skipped.
Oh, okay.
But I can still answer your question. So what you've done is you've changed the species column inside the iris data table. So it's not going to make anything new show up in the environment. Instead, it's just going to change something that's already inside your environment.
What are we changing this?
So this.
So the column names are like.
No, the level. So the levels are the different factor groups.
Right.
So there's species, Versicolor, Virginica, and then you can. This allows you to specify the order that they're recognized in. It's.
In the iris.
Yeah, it's not like the order in the data frame. It has to do more with like. More like over here in the legend. Oh right, yes, yeah.
And then
Yeah. So maybe you want them alphabetized in the legend. but R didn't immediately make them as alphabetized because that's how they show up in the data frame. So maybe, so you could alphabetize them here by using this factor call. And then, yeah, as he's mentioning, when it assigns line types or colors to them, it starts with Setosa, then Versicolor, then Virginica, and that's the order they show up in the legend.
Okay, thank you.
Yeah. Yeah.
Tomorrow we can the break. Then we can explain more.
Oh, yeah, I know. I don't, yeah. It's still long.
Why
2.5.
you would like to use this like graph when you have graph? GraphPad is the program that you make graphs.
I'm not familiar with GraphPad.
Okay, it's like
Is it in R or is it outside of
no,
R?
no, it's like you pay, it's like with license, and it's
Oh,
very easy. You just click the color and what group and how groups, how many groups. It's very
Yeah.
easy. It's like very fast. It's quick.
yeah. We'll see if by the end of the workshop you see why it might be nice to use R to do it and not GraphPad. I don't have a good answer. Like if you already have access to it, like you already have a license and you're happy with it, great. But maybe there's a special use for it that you have that you can't get easily and you can do through R. Maybe not.
So that you know stuff like that.
I've never heard of it. But thank you. It sounds convenient. For install. Oh, yeah, so here is ask you if you want to do it or not. So you just type Y for yes.
But that final, I can go wait till you.
That part didn't run. Interesting. Yeah, someone else is having problems with that line of code. Okay, so let's try this one now, the next one.
This?
Mm-hmm. Oh, yeah, sure.
Do you have the signers?
Oh, yeah, the roster. Shit. There should be a roster floating around the room somewhere.
It's right here.
It's right there. Oh, boy. Yeah, for those of you still in the room, if you don't mind signing them off, it'd be perfect, because, yeah, I accidentally got this to a quarter of you. So we'll just have to do more tomorrow.
It's where and let's try now and putting this in quotes. That had to work. This is where's the double quotes? Is it this one shift? No, I want those ones to look like that. Yeah, perfect. No, it didn't go. Yeah. Try it. It doesn't it's organizing. Do you mind if I? Yeah, you think it'd be in here.
Yeah.
Warning installation. That's different.
Install there. Okay, so we're running the installation again. It might go to a different location. I don't know if maybe where it was saving the package. We'll just do this again. That's okay.
That was a big blast.
That was
a big class.
I have to look into this. I'm not sure why that's happening because I think I was making me think that
They want to know online, will today's lecture be available?
fix it. I have to Google this and get back to you later.
Yeah.
I can't figure it out right now on the spot. This is weird. Yeah, I'm sorry, but hopefully I'll sort something out and email you before tomorrow morning.
Thank you.
Yeah. Do you have a question?
Yeah.
Sure.